Welcome to 7.2 Exponential Growth and Decay and Other Models. So what we have here is we're going to do this again. It was actually in a homework that we just went over earlier this week. Mathematical models in which the rate of change is the variable, or the rate of change of a variable is proportional to the variable itself, are common in both business and scientific worlds. Suppose that the rate of change of y with respect to y is proportional to y itself. This is my rate of change, and we're saying it's proportional, as in proportions are things where you're multiplying or dividing. So we say the rate of change of y with respect to time is equal to k, which we're calling the constant of proportionality, and y is an amount of a substance or an object, something that you're counting, y present at the time t, where y is a function of t. So like a y of t. Okay, so we're supposed to separate the variables and solve the differential equation above. Here's our equation, dy over dt equals ky. And I wonder if we're starting to notice this, pattern with cross multiplying, where we're allowed to just flip those two. Just want to take a moment and say a over b equals c times d. Cross multiply to solve, you end up with a d equals c b. I want to divide by d, and I want to divide by c. So I am going to get rid of this here, and I'm going to get rid of this here. And so what I end up with is a over c equals b over d. And notice that only thing that happened was that c and b flipped positions. So I could do that over here now too. dy over y equals k. And then this piece flips with this piece. I'm leaving the dt. Now, why didn't I flip the k with it? That way there's a constant on this side, so that when I do an integral, I have a little something to integrate with. This is a conceptual piece. I just wanted you to see how the formula gets generated, and it might not actually be a part of the AP exam to generate this formula yourself, but it will be a part to generate an example of the formula. So this conceptual piece, once you do it several times, it'll start to feel more familiar, I promise. All right, so now I have that integral of dy over y, and I have the integral of k dt, and I'm sorry that was too big. I have to make it smaller because I'm saying that the integral of dy over y is the natural log of the absolute value of y, and that will equal kt, and then normally there's a plus c here, but let me just leave that for a second. Oh yeah, there's a c there. Okay, so then I want to solve that, right? And I kind of wish that it was all like at the same height. I don't know why this one's not at the same height. Like this, we imagine there's a straight line here, right? Now, what am I doing? Oh, and why don't I just pull this out in black? Boom, I am taking something to the power of e. Why am I taking something to the power of e? I'm trying to solve for y. Here, what was I doing? I was taking the integral. And then up here, what did I do is I flip using cross multiplying. All right, and why would I try to generate such a nastiness? Well, go back to your make a cheat sheet, take a look at it real quick. Oh, I was already talking about this at some point. Here you go. E to the natural log with an x right there is just equal to x. So if I have an e to the natural log of y, well then I can just replace all of that with a y, and that's what I'm doing. Okay, so now that I have y equals, it is going to equal what? It's going to equal e to the kt plus c, and then I want to, oh yeah, absolute value, of course, absolute value is still there. I want to say that this function has a natural domain, which allows me to take that absolute value off, all right? And, functions of e are greater than 0. Y is greater than 0 is the range. So the range is y is greater than 0. So I can just do y equals. And ready? I'm going to split this apart. Say e to the kt is the function that I'm working with, and then plus e to the c. And so why would I want to do that? Well, it's that the thing is that e to the c is really just a constant. I don't know, like, is it e to the first power? Is it e to the second power? Is it e to the third power? But this is just a constant. And I don't know if you remember this, but my preference is just to treat it like a constant. So I'm really going to say this: y equals c e to the kt. And this c, this is just a constant. And that's the formula now that we get to use. And he's got it right here. Boom. The equation from example 1 is called the basic law of exponential growth or decay. And C is the initial value of whatever you have. And he says substance, which is whatever you're counting, so, or whatever your population is. K is the constant of proportionality. If K is greater than 0, what we have is growth. If K is less than 0, what we have is decay. Growth, by the way, looks like this, and decay, by the way, looks like that. And t is the variable for time. Y is the amount of substance present at time t. Let me just focus on example 2. I've erased all that other stuff. What is the rate of growth of the population in a city whose population triples every 100 years? So I'm trying to just imagine this situation where I have some time and I have some sort of population growth, okay? So I'm saying like y of t. What will be my my population growth? So I'm saying then that when I start with no time at all, right, 0 time, initial amount, I'll have some sort of population here. And then after 100 years, I'm going to have 3 times that population, okay? Now, going back to this whole equation, y equals c e to the kt, that's called the basic law of exponential growth or decay. And he says that this can be modeled using this thing. So I'm going to say then that y is going to be my 3 population. And then don't forget, c is my initial value. So that's going to go right here. And then I'm calling this e, ready, to the kt. Now, what you might see another professor do, and I wanted to show it to you, is they might just do this, ready? They're going to call this a c. You know, the population, they're going to call that a c. So it's 3c equals c e k to the kt. And then, by the way, we can divide by c, we can divide by c. And so now we have 3 equals e to the kt, and we don't know what the population is. We just know that it tripled. Oh, isn't that interesting? It's because that's the thing. What we're talking about is that there's some sort of proportionality, and the proportion here is 3. Okay. Anyway, I know that's not where I'm, that's not where I'm putting K. And in fact, I'm going to say in his notes, and I don't want you to be mad at me. He says in his notes to use an R, and it's not a K. Like, well, why are we not doing R? Like, K was already a problem for me. Why would I want to just randomly change all these things into R's? You can leave them as K's. It doesn't matter. It's just a variable, but he went to R because it says rate, So right here, you could say R equals the rate. And now when we are solving stuff, we're getting in there. We're trying to figure out what that rate is. By the way, we also do know what time is going to be. So we're substituting in that T equals 100 when we're trying to solve this thing, because we're still looking for the R. So now I'm going to go right to here and I'm going to say 3 equals E 100 times R. Okay, 100 times R. Now what? Well, we got to break out that rule with taking it to a natural log. Like, I'm trying to get R to be by itself. So I'm applying a natural log here and a natural log here. And so I get to keep the natural log of 3. But the natural log of e with a power, that power comes out in front. So I have 100r. And then the natural log of e is the same thing, ready, as 1, so it disappears. Now, just to remind you of those rules on the mega cheat sheet, again, we're in here on these important little rules. They're very small, but they're so important. So the power rule with a natural log is that p comes out in front, and that's what we've done. And then the other thing that we have is that the natural log of e is equal to 1. So we're using this very special rule, we're using that very special rule, and we already used that special rule in the part above. So now I have 100r equals the natural log of 3, and I'm going and I'm saying that my rate is going to be, ready, the natural log of 3 divided by, because if I divide by 100 here, divided by 100. All right, that's my rate. But I need to express it as a percent, which is rounded to the nearest 100th of a percent. And here's the thing, if I wanted to express r as a percent, then what do I need to do to change this, constant is I will need to, ready, divide it by 100. I'm already dividing it by 100. So it turns out that the r written as a percent is really just the natural log of 3. Okay, it's really just the natural log of 3. This is a percent for me already. So I can put it in here, and I will say then, put it in here, put it in where? Oh yeah, put it in here. I'm sorry, that's not open. So what is the natural log of 3? What is the natural log of 3? The natural log of 3, there's my natural log, there's my 3. Do a control, do an enter, and that's what you get, is 1.098. And here's the thing, he says here to the nearest 100th of a percent. Remember that here, that's a 1%, that's a decimal, that's a tenth. This would be the 100th. And in that case, I'm going to do some rounding. So I have 1.098, which means I'm going to say it's really 1.1. So my rate equals 1.10%. He said round it, so we're rounding. That's just so you can understand that that's what we got is a rate of growth that is 1.10%. So a tenth of a percent. Now, if you look back on this, it makes sense. Every 100 years, if you go up by a tenth of a percent, if you multiply that by 100, it looks right. You know what I'm saying? That makes sense. All right, so we're coming back to example 3 now, and it says, let y represent the mass in pounds of a radioactive element whose half-life is 4,000 years. If there are 2,200 pounds of the element, sorry about this, in an inactive mine, how much will still remain in 1,000 years? Express your answer to 3 or more decimal places of accuracy. That's the AP rule. So we're at least, yay, going back to the AP rule. So we have our rule. We're solving for K. All right, remember that was our first step. So we're saying that half-life means that we're multiplying by half, which is the same thing as 0.5. You can use either a half or 0.5. In our lecture notes that I'm using, he's using 0.5. So we say that we had a C and it was equal to K. And then how about it? Our time here was what? Half-life is 4,000 years. So our time here is going to be 4,000 years. 4,000 years. That's going to be equal to e to the kt. That's going to be equal to t. And then over here, I'm going to have my 0.5 times c. That's a terrible decimal. There we go. We can divide by c on both sides. And so now we have 0.5 equals e to the 4,000 k. and I want to take the natural log of both sides. There's my natural log, there's my natural log. And I will then say that I have the natural log of 0.5 equaling 4,000k. And then I want to solve for k, so k is going to be equal to the natural log of 0.5 divided by 4,000. So I'll put that into my calculator. K. Oh, I feel like there's a variable, a way I can define a variable. Like k is going to be defined. No, this guy. No, this guy. Hold on a second. I need my keyboard. There we go. Defined as being, ready? What did I defining it as? The natural log of 0.5 divided by 4,000. What is that, by the way? It was a very small number, okay? So now I have k, and if I type in that k, it's bold, and hit enter, it'll tell me what it is. All right, cool. And now I want to go back to my problem, and I'm not writing down what k is because I really don't care. But my second step is to solve for y. Solve for y. And remember that my formula was looking like this. Y equals, and we found out at the beginning that we wanted to have 200 pounds of this element. So there's a 200 here, because that's going to be my constant where it's my initial amount. I divided by it, so it wasn't a part of me finding that k, but I'm going to create the equation now. So I want to put it back in there. That's my c. This is e. There's a k, which I do know what it is. Boom, I do know what that is. And then I'm multiplying by that 1,000 years because we wanted to check what was happening at 1,000 years. After 4,000 years, I would have 100 pounds, right? After 4,000 years, I would have 100 pounds. So I wanted to know what's happening after only 1,000 years. Okay, not going to have as low as 100 pounds, but how many pounds will I have? So I'm coming over here to my calculator, and I'm going to type it in, and I'm saying I have my 200, and I have my e, and here is e, and there's a power for it already for me, and I'm just going to type in that k. It's bold. It knows what k is, and then I'm multiplying that by 1,000, and oops, my bad. I don't want to change that. Look, I need a multiplication symbol there. I need 1,000, and then I hit control, and then I hit enter. Now, what you need to do is go and try this problem again and actually put it into your calculator. So just like pause and try to do this whole problem again on a sheet of paper with your calculator so that you know. And by the way, when you do that, you can then write down with certainty and confidence this is going to be equal to 168.179 pounds. And that's the answer you would put down in the AP exam because it has 3 decimal places of accuracy. And I did not do any rounding. It wasn't necessary here because that was a 2, but even if it was, I would not have done any rounding. And that's how you use the calculator to help you get the answer to this. Okay, now we take a look at Newton's law of cooling, which this paragraph's a bit, let's just read it slowly, states that the rate of change in the temperature of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. Supposing a metal figurine heated to 150 degrees Fahrenheit is brought into a room having a constant temperature of 72 degrees Fahrenheit. If the figurine cools from 150 to 215 minutes, how long will it take for the figurine to reach a temperature of 100 degrees Fahrenheit? Let y equal the temperature and express your answers to the nearest minute. Now, I'll mention in his notes on this topic, there's like a line missing in our in this space right here. So I'm going to put it down. But before I do, let me just try again to make sense of the problem. I'm just going to put down a little table of values that I got here. T's and y of t's. So we are going to say that we have this object at time 0 that weighs 150 degrees. That measures 150 degrees Fahrenheit. Then after 15 minutes, it cools down, and it cools down to 120 degrees. How long will it take for the figurine to reach a temperature? And so this is our question mark. This is what we're looking for, to reach that temperature of 100 degrees. And I think we're going to use all of these facts. Now, so what he says in his notes on this is to start, ready, with dy dt equaling k times, well, it's supposed to be y, right? But the difference between the temperature of the object and the temperature of its surroundings is what the Newton's law of cooling says. And this is obviously a physics problem. You would see this, when you go to college and you take a physics class. So hopefully you're going to feel like it's really worthwhile for me to go over it with you now, so that you get a hint for how to handle it when when you're going to get obviously a few more complex questions, like this one isn't already hard enough. Y minus 72 is what I'm going to put here. What? Why? Well, the formula normally would have a y here, and since I'm doing a difference between whatever y is and that constant temperature of 72 degrees, this is where I'm getting. Now then, again, in his notes, and I'm going to tell you right now, this part's optional, okay? Because we already have a formula for y, don't we? We already have a formula for y, and I'm going back and I'm looking at it, and I'm saying that is y equals c times e to the kt. So our formula should be y minus 72 equals c times e to the kt. And I'm just saying, in his notes, he's showing you how this information here turns into that. But I've already gone over it in this video, so I think you'll know. So if you want to skip ahead to when I erase this section, you're allowed to. Okay, so go now. The integral of so we cross multiply, we get we cross multiply, meaning that we flip, and we have that dy over y minus 72, and that's going to equal, k is still over here, but dt moved for us. And then, like I said, every time I'm going to throw an integral symbol down, I'm going to do it in a different color, so you know that that's a different step. And then I would like to integrate this, and I'm going to get the integral of the natural log of the absolute value of y minus 72, and that's going to equal kt and plus c. And then I want to take it to the power of e, which again I'm doing in a different color, and this part is disappearing for me, which was my goal. So I have the absolute value of y minus 72 equals, ready, e to the kt plus c, which we then say to ourselves, we don't need these absolute value symbols because our temperatures are all positive, and so we have y minus 72, and we don't need this version of it because we know that e to the c is a constant, and so we just want to have we want to have c out in front with an e to the kt, and now I get to just use that formula, which I told you I would. Okay, so I'm actually not wanting to put this in this space. If you have more room, then you're good, but I run out of room. You guys know I do. So I'm erasing it, and now you know where that formula comes from and how I'm going to use it. So ready? The formula again is y minus 72, and that equals c e k to the kt. And, for funsies, if you wanted to try and derive this formula yourself, that'd be great. So now I'm saying that I'm using these initial values, okay? I'm going to use some of these values to help me figure out some more stuff. And so the first, remember, he has steps. First is to find C. And how are we going to find C? We're going to use this first value right here, and we're going to plug it in. So I have 150 minus 72, and that equals C and E. And then this is ready, K times T, so K times 0, which is just E to the 0. So 150 minus 72 is 78, and that equals C, E to the 0, and E to the 0 is technically equal to 1, so I just found out that C equals 72, okay? Sorry, I keep doing this, I apologize, 78. And then I want to have my second step now to be to find K. And I'm hoping that this will help me do that because I put back in, right, y minus 72. Oh, sorry, 120 minus 72. And that will equal, here's the 78 that C was. And then I have E, and I'm going to multiply K times, ready, that 15. And so how do I go about solving for that? Well, first of all, I'll figure out that 120 minus 72 is 48. And then I have a 78 here, and I have an E and a 15K. And I want to divide by that 78, and I want to divide by that 78. And then I want to have apply a natural log. And I'm applying the natural log in a new color. The natural log of 48 over 78 will equal, that part disappeared, so I have a natural log of e to the 15k. I hope you don't mind, but I could just write down that 15k now, right? And then I would say that in order to find k is going to equal, and I like the blue better, so I'm going back to blue. So I have k is going to be equal to the natural log of, ready, the 48 over 78, and all of that needs to be divided by that 15 that was this 15k. And now I got to go into my calculator and I need to find that. So I'm hitting buttons here, and if you want to see me hit them, it's on the left, and they're red. So I have the natural log, whoops, let me get there. So I have the natural log of, what was it again? 48 over 78. 48 divided by 78. And then I'm dividing all of that, ready? I'm dividing all of that by 15. Let's put a division symbol there. And then I'm going to hit Control, and I'm going to hit Enter, and boom, that's what I got. Only thing is that I really like to save that value. I might need it. You know, the notes are telling me that knowing what K is pretty handy. So I can do it after the fact, by the way. I did already define K previously in this video. So if you want to, you could just change to another variable, but I'm going to redefine it. I'm going to overwrite what it was before. And how am I going to do that? I don't want to type in the whole thing all over again. So I'm just scrolling up and I'm hitting enter, and there it is. And then I'm going to hit enter now. And that's what K is defined as. And so if I hit K and then I hit Control and enter, do I get the same thing as I did before? Yes, I do. And it is all done for me. So now I know what K is. I'm going to go ahead and use that. So this was step 1 right here where we found C, and then this was step 2 right here where we found K, and step 3 will be, ready, number 3 will be to use this point T and 100. And by the way, I do want you to do a little bit of error checking on your work. You're expecting your time to be sometimes not too long after 15 seconds, right? Because you're only going down to 100 degrees. So I just, you can do a little error checking there to make sure that when you get your answer, like, does it make sense? All right, so I'm saying that I have 100, that's my y, minus that 72 that was in my formula, and here's the 78 that was my constant C, and then I have E, K to the T. And I love this in his notes. He's like, doot, doot, doot. And so we say, right here, we say store K and use later, right? So we've stored K, and it is bold when we type it in. And that was a terrible looking E. Okay, so now I'm going to put it into my formula over here. And by the way, I don't want to, I don't want to do any more algebra on this. If I can get away with just solving for K, then that's what I'm going to do. So I'm saying then that my formula has a T in it. So I have my 100 minus the 72. I'm not doing any arithmetic here either. That equals 78. And then I have my E, ready? Boom. And it was to a power of K and T. And, let's put a multiplication symbol in there because I don't want it to forget that that was a constant. I want it to stay bold, just like E stays bold too, because E is already defined as something as well. Comma, T, and then I'm going to hit Control and Enter, and I now have a time, which is 31 minutes. So, wow, that was a little bit longer than I thought it would. Okay. So we would round that. If he says express your answers to the nearest minute, I would round that to 32 because 31.6 rounds up to 32. Now, I'm saying that this is great if you're allowed to use a calculator. If you're not allowed to use a calculator, then you would have to do this algebraically. And your answer would be best done on the AP exam in the following way, okay? So we have that 28, and that equals 78 e to the kt. And by the way, I defined k right here. This is a definition, and I do not have to rewrite this portion in the AP exam. You know how I just showed you guys a paper where you were like, there was part A and there was a box for you to write an answer. There's part B and there's a box for you to write an answer. If you defined K up here and you said that it was some, expression, then you can use K down here and not have to redefine it. The job of the grader is to go back and look to see what did you say that K was. And get this is very important. You do not get points off if this K is wrong. If this K is the wrong number, it's okay because you used it here and you lost some points, right? Because it wasn't correct. Well, you won't lose points here. You will get to keep the points as long as you keep just this K and you don't rewrite the thing that was wrong. If you don't because here's the deal, you're only supposed to get a point taken off for the mistake one time. You're not supposed to get consecutive points being taken off because that thing was wrong. So somebody had said something to me during the test, like they were like, but if I get this wrong, then I won't be able to get the next ones right. Nope, they don't care about that. So now I'm going to divide by 78. I'm going to divide by 78. I'm going to say I have e to the kt, and that equals, ready, 28 over 78. And I'm wanting to apply a natural log to both sides. So the natural log and a natural log. And I'm throwing my absolute value on there. You know what? I don't even need the absolute value. I'm gonna leave it off. So then this part disappeared, and I have kt equals the natural log, and here's the 28 over 78, and then I'm going to divide by k. I'm going to divide by k, and I can now say that t equals, ready, and this is what it equals, and this is exact, and if I did not have a calculator, this would be the answer that I would give. It'd be 28 over 78 divided by k. Do you like that? Or maybe, I would feel a little bit nervous about it. I'd want to put brackets around it. I suspect it's fine without the brackets, but I just do love to add extra brackets to make sure that they know that I know that the whole thing is being divided by k. All right, there you go. That's your answer. 32. Oh, so, I messed up. I missed something. I missed something important. Ready? Minutes. Don't forget your units. Minutes. You got to put that in your answer. Don't forget. You're like, I have everything done. I'm going to leave it. I don't have a calculator. Sure, you're going to leave it because you don't have a calculator. But don't forget to write down the units because units are worth stuff too. Good luck on the homework, guys.